Well, today's topic is acceleration. Let's review a little bit. What we've seen already is that the slope of a graph of distance versus time is the speed. And we can think about this in two ways. If we look at this graph of distance versus time, if we pick one single point and draw a tangent through that point, that slope of that tangent is what we call the instantaneous speed. That's the instantaneous speed. However, we can pick any 2 points on a graph and get a sort of an estimate, or what we might call the average speed, measuring the slope of the line that goes through those points. So that's average speed. Another thing that we've learned is that the area under the curve of a graph of speed versus time is the distance. We've used this to solve several kinds of problems. There's time, here's speed up here, and let's say that we had a graph that looked like this for constant speed. Well, that rectangle is just a classic equation, distance equals rate times time. Or we've also looked at situations like this one where we have a triangle, and we find the area under that triangle by 1/2 the base times the height, and we were able to get the distance. So the area under any graph of speed versus time comes out to be the distance. So here's what we could say. When the speed changes constantly for an object that starts out at rest, since the area of a triangle is 1/2 the base times the height, and the height is what I'll call VF here for final velocity, and the time change here is delta t, whatever that time change is, it gets up to final velocity. Well, that product divided by 2, we could say, is our distance. And we've used that equation to solve a number of problems. Well, acceleration, we can define this as the rate of change of speed with respect to time. Rate of change, we're talking about slope here. We can define this as speed change over time change. That would be a definition of acceleration that uses symbols. How much does speed change over how much time it takes for that speed to change? If you have time versus any variable on a graph, the slope of that graph is the rate of change of that variable with respect to time. For example, we've already seen speed is the slope of distance versus time. So thinking about acceleration, what would the graph be whose slope would represent acceleration? Well, if acceleration is defined as the rate of change of speed with respect to time, then we would be graphing speed or velocity versus time. So the slope here, that's acceleration. Change in velocity with respect to time. Well, we're going to develop a few equations here, 3 equations really. 2 of them are very powerful and universal. And we're going to start out by looking at something that's more of a special case, and then we'll expand on it. We're going to develop an equation that tells us the distance that's traveled while an acceleration takes place. And we're going to look at the simple case. We've actually already developed this really. For a constant acceleration when the object starts from rest, the distance is, as always, the area under the curve. So if it starts at 0 and it goes up to a final velocity v, and it does this over some time that we're going to call delta t, well, then the distance is 1/2 the base times the height, which would be v final minus 0 times delta t, change in time, over 2. Or we could also say this another way. Since Vf minus 0 is really change in velocity, we could make this slightly more universal by saying delta V instead of this. Instead of Vf minus 0, we're going to say delta V, change in velocity, times delta T, and then divided by 2. So let's look at the more general case where the initial speed isn't necessarily 0. This will solve more problems and give us an equation that's more valuable in different kinds of settings. So here's a graph that would depict such a setting. We're going along at speed v initial, not at 0. So we're cruising along at this speed here, and then at time t initial, the first starting time of the change, of the acceleration, we see the speed changes. That's acceleration. We're accelerating through this period. And then we go up to t final. Well, v final actually should be on this graph up here someplace to correspond with the velocity at time t final. So how much has time changed? Well, it's changed delta t. How much has speed changed? Well, it has changed delta v. V final minus v initial, or delta v. Well, if we want to know the total distance covered, which is our objective here, probably the smart thing to do is divide this region here that we have through delta t into two simple geometric forms. The first one is a rectangle, and that's easy. The distance here is just going to be equal to vi times time. Well, here our distance is going to be, for the triangular region here, distance is going to be equal to vf minus vi, that's the height, times the base, which is delta t, all divided by 2. Or we could say delta v times delta t divided by 2 is distance. Well, all right, so here's an equation. The total distance, or the total area, is going to be equal to the area of the rectangle, which is vi times time, plus the distance of the triangle, which is delta v times delta t over 2. Now let's think about our definition for acceleration. Up here I'm going to write this down. Acceleration we defined as delta v divided by delta t. So that means delta v, we just multiply both sides by delta t, delta v comes out to be a times delta t, acceleration times delta t. So I could substitute, instead of delta v down here in this equation, I could write acceleration times delta t, because they're equivalent, they're the same. Which brings me to another equation. I'm going to write this one down here. Total distance is going to be vi times t plus acceleration times delta t, that's what we're calling delta v now, times delta t again. So delta v is a delta t times delta t. That's all divided by 2. Or we could simplify this and say d equals initial velocity times delta t plus acceleration times delta t squared, but that term's divided by 2. So here we've got a sort of a standard universal form that physics students all learn for figuring out what's the distance that's covered by an object as it undergoes an acceleration, even if it isn't starting at 0 for its initial velocity. So here it is. This equation in a box is a pretty good cue for you that this is something that you're going to want to remember. If you haven't done it already, I would start a toolbox, an index card, or probably a larger sheet of paper that I just write down these equations that you're going to see in boxes, because they're great tools for problem solving. You want to have them at hand when you need them. Here's an example problem that we could use this equation to solve. Let's do analyze, plan, compute, evaluate to get through this problem. A ball is traveling at 2.5 meters per second. So what's that? This is the analyze stage here. What do I know? I know velocity initial is 2.5 meters per second, and it accelerates at 1.4 meters per square second. All right, so acceleration A is 1.4 meters per square second. That's something else I know. Here's something else I know. 15 seconds it's going to travel. The question is, how far will it travel in 15 seconds? So delta t here is 15 seconds. And what do I want to find? Well, the question is, how far? So that's a D. That's my unknown. That's my analysis. Here's a plan. Remember, when you're making a plan, you're looking for an equation that links the stuff you know to this thing you need to find. Well, we have that equation. It's distance equals initial velocity times delta t plus acceleration over 2 times delta t squared. It's the equation that we just developed. Now we compute. Got a plan. Plug in some numbers. Distance is initial velocity. Well, that's 2.5 meters per second times delta t. Delta t is 15 seconds. Plus acceleration over 2. Well, the acceleration, it says, is 1.4 meter per square second divided by 2 times delta t squared. Delta t, remember, was 15 seconds, so we're going to square that. Now, part of the evaluation step happens as you're computing. Take a look at the units. Find out what's going on here. Seconds are on top and bottom here. Seconds are going to cancel out. Here I'm squaring seconds. That gives me square seconds, but my unit of acceleration is meters per square second, so that cancels the seconds out again. So it's meters plus meters. So my unit here is going to be meters. Well, let's actually do the calculation and find out how this works out. Expand my calculator a bit. 2.5 times 15 plus 1.4 divided by 2 times 15 squared gives me 195 meters. Okay, the last step always in problem solving like this is the evaluate step. So we'll evaluate this answer. Well, the easiest part of evaluation here, and the one that's most sure for us, is meters are the unit. It's supposed to be distance. Meters is the unit of distance, so probably things went right. Not many of us are probably going to have a really good feel for balls moving at 2.5 meters per second and how far they should go in 15 seconds. So it's hard to get a common sense test on this one.